Hi, this is assignment 3 by Group 3 by Travis Roller, Caleb, and Jack.
For question 1 of our assignment, we were told to find the number of vacancies in both copper and palladium, which were our metals 1 and 2. To get the total number of vacancies in a centimeter cubed of copper, we were able to use the equation NV equals N times E to the negative QV divided by K sub B times T, where NB is the total number of vacancies, N is the number of lattice sites in the metal, Q sub V is the energy required for vacancy formation, K sub B is Boltzmann's constant, and T is temperature in Kelvin. To get N, we can use the equation V times rho divided by M times NA, where V is the volume, which was 1 centimeter cubed, M was the mass of the metal, rho was the density of the metal, and Na was Avogadro's number. With this, we're able to get the number 7.959 times 10 to the 24th centimeters cubed. Using the same equation from the previous slide, you can get the number of vacancy defects for centimeter cubed of palladium, which was 7.853 times 10 to the 15th centimeters cubed.
Alright, and for question number 2, we have two formulas to find the Frenkel and Schottky defects. So, to find the Frenkel and Schottky defects is represented by N equals number of atomic sites exponential to the energy required to form a defect in electron volts divided by 2 times Boltzmann constant times temperature. And then the second equation down here is to find the number of lattice sites in our metals, and that'd be represented by big N and Na, which is Avogadro's number, which is 6.02 times 10 to the 23 atoms per mole. The density of our material, which is in grams per meters cubed. We have to make sure to do our proper conversions for that by getting it from grams per centimeters cubed to grams per meters cubed. And then the atomic mass of our elements 1 and 2 for our semiconductors. And that's represented, and those are found from the periodic table of elements. Alright, so to find the Frenkel defects for our semiconductor gallium nitride, a Frenkel defect is a cation that moves into an interstitial site, and that's represented by the formula number of defects equals N exp activation energy over 2 kT. But first we have to find the number of lattice sites, so we do that by inputting our givens. So we input Avogadro's number, our density, atomic masses, and then we can find our interstitial sites of 4.35 times 10 to the 28 lattice sites per meters cubed. And then we plug that into our main formula to find the number of Frenkel defects by doing number of lattice sites to the exp of 5 EVs divided by 2 times Boltzmann constant temperature, and that gives us 5.55 times 10 to the 18 defects. And then to find the Schottky defects, it's the same formula but just a different activation energy. So that's represented by 6 EVs. So we would input 4.35 times 10 to the 28 lattice sites exponential negative 6 EV divided by 2 Boltzmann constant and temperature of 1273 Kelvin. Now for our semiconductor aluminum nitride, it's the same procedure to find the number of Frenkel defects. So firstly we have to find the number of atomic sites by inputting our givens. That yields number of sites 4.79 times 10 to the 28 lattice sites in a cubic meter. And then to find the Frenkel defects, we do the same procedure, input our givens, and that gives us 1.0 times 10 to the 36 defects of Frenkel defects. For the Schottky defects of aluminum nitride, it's the same procedure as before, except with another activation energy of 5 eV. So again, we input our lattice sites, which is 4.79 times 10 to the 28 exponential negative 5 eV divided by 2 Boltzmann constant in temperature. And that gives us 6.10 times 10 to the 20 times 10 to the 18 defects per meters cubed.
So next we'll be looking at question 3 of assignment 3, and we were asked to find the diffusion length of carbon in copper for 1 minute at 300 Kelvin and at 600 Kelvin. So from the article that the professor sent us, diffusion length is the average length a carrier moves between generation and recombination, and this is calculated by taking the square root of the diffusivity times the lifetime in seconds. So the lifetime for this problem would be the 60 seconds or 1 minute, and diffusivity can be swapped out with diffusion coefficient, and you calculate diffusion coefficient by multiplying d naught by exponential negative qd divided by rt, where where d naught is the temperature independent pre-exponential, qd is activation energy for carbon in copper, R is the gas constant, and T is the absolute temperature. So looking at the table on the bottom, you can see that at 300 Kelvin, the diffusion coefficient would be 3.34 times 10 to the negative 42. The lifetime would be, again, the 60 seconds. So plugging those into the diffusion length formula, you get a diffusion length of 1.42 times 10 to the negative 20 meters. And looking at the next row down, at a temperature of 600 Kelvin, the diffusion coefficient would be 8.86 times 10 to the negative 25 meters squared per second. Again, the lifetime would be 60 seconds. And plugging those into the diffusion length formula, you get an answer of 7.29 times 10 to the negative 12 meters. Part 2 of question 3 asked you to find the diffusion length of silicon in your semiconductor A. Our semiconductor was aluminum nitride. So again, it's the same formula as from the previous slide. Diffusion length is square root dt, where t is your lifetime in seconds, and d is diffusivity, but that can be again substituted for diffusion coefficient. And diffusion coefficient is again d naught times exponential negative qd over rt. qd again is activation energy for silicon in aluminum nitride. R is the gas constant, and T is the absolute temperature. So looking at the bottom table, similar to the previous slide, at a temperature of 300 Kelvin, the diffusion coefficient would be 1.51 times 10 to the negative 27 meters squared per second. The lifetime, similar to the previous problems, would be 60 seconds. And plugging those two values into the diffusion length formula, you would get a length of 3.01 times 10 to the negative 13 meters. And at a temperature of 600 Kelvin, you would get a diffusion coefficient of 5.96 times 10 to the negative 15 meters squared per second. Lifetime 60 seconds again. Plugging both of those two values into the diffusion length formula, you would get a length of 5.98 times 10 to the negative 7 meters.